Well, it's 5 till, and I'll get us started so we can keep working through. We have a lot going on a good time schedule to get to the next test. Now, after the test, it's going to be a little tight trying to fit those two little chapters in there, so probably have to do like half of one and half of the other one. But we'll worry about that after the exam. But I thought I would start then by reminding you have an exam coming up. It's a week from today. And so that's what we've been working towards. We did Chapter 11 on Monday, as you recall. I think we did one example and then kind of a hinting towards an example that you have as a homework problem. In fact, I want to come back to that. I want to do 2 examples first and then jump back to that hint. And then 2 other examples after that, if I'm counting right here. 1, 2, 3, no. So a total of 5 more examples would be great to do, and then kind of a hint or a discussion about 36. I don't know if you want to call that 6 examples. But the idea here is to do a bunch of examples with momentum. I told you it was a short chapter. Angular momentum, that's the new feature of the chapter. And then we'll jump into Chapter 12. So hopefully we can even lecture on Chapter 12. And Chapter 12, as you will quickly see, is another very short chapter. There's no new physics in it. That's why I said on Monday, I like the ending of Monday, meaning that you're not going to learn anything new between Monday and the exam. And so that gives you 9 days for this stuff to kind of settle in and digest. And I think you did a lab on, a good lab is what I should say on it. I know you did a lab on it, but a good lab in the sense that you did conservation of angular momentum in 3 different experiments. And each of them ones dealing with, excuse me, some of the harder things. So that's where I want to pick up. So simply put, examples, 6 examples here from Chapter 11, jump into Chapter 12. And if we are so fortunate to get done with talking about Chapter 12, then we'll start examples on Chapter 12, although I don't really see that happening. So I see us doing examples from Chapter 12 on Monday, and then also another lab related to Chapter 12 on Monday, and then the test on Wednesday. All of that is to add to the fact that don't forget your extra MC class is, well, besides Friday, so maybe I should throw that in there too, is Friday, but then an additional class then is a review on Sunday. So, you know, your exam being 7 days away means you've got 2 class periods, a lab period, and 2 MC periods. So a lot of opportunities to learn the material here. So make a note of it, Sunday 1 to 4. As Don always does right in here, PS 130, so nice review. And test number 3, chapters 9, 10, 11, and 12. I did want to say this as I got started, as I was looking back and I realized, you know, we've been making this long chart for the last 2-3 weeks of comparing, well, 3 would be too long, but comparing translational motion with rotational motion, and saying this was the idea of Chapter 10 mostly, but then carrying over here into Chapter 11, that everything we did for translational motion we now repeat. And as we repeat them, it gives us a chance to review the old stuff, and hopefully it makes understanding the rotational stuff a little bit easier. And as I was thinking about this long chart, I think there was one, a significant one here, that was missing. And maybe it was so obvious it didn't need it, but I got to thinking about it. I said, no, it's not so obvious. I should put it up here. And the one I'm thinking of was the one that showed up at the very beginning of Chapter 9. And so maybe that's why I kind of forgot about it, because it was, you know, I was doing everything from chapters 1 through 8. But in Chapter 9, we did have the introduction of linear momentum. And we came up with this, that the net force is equal to the change in momentum with time. And if you remember working that one out, we did this. We said, well, let's start with Newton's second law, and then look a little closer at it by saying it is a derivative, move the mass back inside, and then we have this equation. And so we started Chapter 9 with what we called an alternative look at Newton's second law, and say the net force changes the momentum of it. But what was important about that statement here is, what if the net force is equal to 0? What does this statement say? Yeah, that's our conservation of momentum. It says then, and I guess these are really vectors here, but it says that your momentum is a constant. In other words, from your calculus class, you know the derivative of a constant is 0. So if you have no net force, that's when you have conservation of momentum. And so the question we had at the beginning of chapter 9 was things like, is the momentum conserved or is it not conserved? And so we had something as simple as, you know, an object like this pen hold up here. If your focus is only on the pen and you let it go, you would say, no, you don't have conservation of momentum. You would look at it and say, is there a force on it? Yes. And so does its momentum change? Yes. That's what this equation is saying. And then, of course, as it falls down, you can watch it go faster, faster, faster. Its momentum is gaining. Of course, if you expand your view and we did a system and we say, okay, let's look at the pen and let's look at the Earth, and you look at the two together, and you would say, okay, well, the Earth is pulling down on the pen, but the pen is pulling up on the Earth. Together, the net force on the system is 0. So together, the change in momentum of the system is 0. And I didn't really emphasize that as we got into chapter 11 here, because we need to really do the same thing for rotational objects. So that's why I thought today might be a good time to go back and review that. That was our logic behind conservation of linear momentum. And so we have to ask ourselves, when is momentum conserved? Well, linear momentum is conserved when there's no outside forces. And so as we do the problems, we have to say, well, take a look at how you're setting up the system. Are there any external forces? And if the answer is no net external forces, then the answer is the momentum is conserved. But if there is, like this pen, if you just look at that pen, then you would not try to use conservation of linear momentum. Fair enough? Well, the same thing is also true for rotation. So let me emphasize that. Let me start here. Let me start with the idea that angular momentum equals r cross p. And now let me take the derivative with respect to time. And you can hopefully kind of see why I'm doing that. If you compare this to what we did for linear momentum, this, which is the derivative of linear momentum with respect to time, looks like this, the derivative of angular momentum with respect to time. What does it equal? Well, this might be a little harder derivative to do because it does have two pieces to it. But again, you know how to do a product rule, although you may have never done a derivative of the product that is the cross product of some vectors. So I go, well, maybe we better go through this for the first time. But it's really the same thing you did in your calculus class. If you remember, you would take the first times the derivative of the second, plus then you would leave the second alone and take the derivative of the first, right? So there's your product rule. So no different other than I'd leave it as cross product because they're vectors. And also be careful not to reverse the order because as we saw last lecture, the cross product depends on which one you put first. And you switch the order, you switch the plus and minus sign. So I was careful not to switch the order. And then it falls into place. It still may not be quite so easy to see. I'll start here. This first term is r cross, and what would you call that? There's your F. And then, and more on that in a second, this one I think is both easier and harder, if that makes any sense. Because the answer is real easy here, but it may not be quite so quickly to see. Anybody see the answer to this one? Yeah, I heard somebody say 0. Why? They're parallel, right? This is really the velocity vector. This is mass times the velocity vector, right? They're both in the direction of the velocity vector. And how do you calculate cross products again? This would be the magnitude of the first one, v, times the magnitude of the second one times the sine of 0 degrees. What's the sine of 0 degrees? 0, yeah. So two vectors in the same direction. The whole idea of a cross product was saying how much of one vector is perpendicular to the other. And so if you ever have two vectors in the same direction, you take their cross product, you're going to get 0, of course. Because there's none perpendicular. There's none amount that is perpendicular. So that one goes away. So that's why I said that's the easy one, right? Okay, well, once you realize it's two vectors in the same direction, it's easy. But if you see that, then what this boils down to is just the first term. Now let's look closely at that first term. What is that first term telling us? And hopefully you see net torque. And so, yes, the mathematics was a little more involved because of the cross product and the chain, the product rule when you take the derivative. But hopefully not a surprise when you finally get to the end product here. Doesn't it say, just like for translational motion, the net torque is equal to the derivative of the angular momentum. So, derivative with respect to time of the linear momentum is the net force, or put another way, net force, if there is one, changes the linear momentum. Same thing here. Net torque, if there is a net torque, it would change the angular momentum. If there's not a net torque, it wouldn't change the angular momentum. Okay. You might remember, it's worth throwing it up here again, when we left class and we needed it for the lab problem that we went in to do, because we took an object and we shot it. We said the object had a mass m, it was traveling with a velocity v, and in our case we had a little track over here that was on a rotating axis, and the ball had this little catcher in it, and the ball caught it. And of course what you had to do was to say that the initial angular momentum is equal to the final angular momentum, right? And of course we left class with the idea that if this is your calculation for calculating your angular momentum, and that this distance is d, then we came up with dmv for the amount of angular momentum of an object going in a straight line. And so that was where this r cross p came into play. I'll do it again real quick. We said, all right, if you go to calculate this, the initial angular momentum, you would go r cross p. Now, not worrying about direction here, this would be the magnitude of r times the magnitude of p times the sine of the angle between them. So this is r mv sine phi. And what I was trying to show you, and want to expand on it now, is that if you look at this r coming out, this is that angle phi, and if you put the r and the sine phi together, you get that d times m times v that we, like I said, derived at the end of the class, like we'll need in a few moments here, and like we did at the lab, is there is the angular momentum of an object going in a straight line. I did want you to notice that as the object continues to go in a straight line, if you recall, this was just an object going in a straight line with no forces. So if it had no forces on it, we could say, well, its momentum wouldn't change. Now, I think you already know that. That's not what this chapter is all about. That's chapter 9. If you have an object with no forces on it, it's going to keep the same momentum. So it just keeps going with the same velocity in the same direction, and you get the same momentum. But what I also want you to see is if that object had no forces on it, it would also have no torque. So what would you say about its angular momentum? It would be a constant also. It shouldn't change. And so notice that as the ball moves to different locations, the r is going to change, the angle is going to change, but they're always going to change in such a way that when you take the r and you multiply it by the sine of the angle, you're always going to get d. And so no matter where this ball is, you will have the same angular momentum. And so as this ball travels in a straight line, not only is its momentum conserved, but its angular momentum is conserved. We have no net force, and we have no net torque. And so that's what we'll be looking at as we do some problems. And in fact, when we got started with Chapter 11, I said, well, go ahead and imagine maybe the solar system where you put the sun and maybe some kind of more elliptical orbit. And so I'll give it a lot of the elliptical orbit, so it's certainly far more elliptical than the Earth's orbit. The Earth, if you don't already know, it does have, it is an ellipse. All of our orbits are an ellipse, but the Earth is not that ellipse. Do I let it fly by or kill it? All right. It's not that ellipse. So this is a much more elliptical. Maybe I'll pick on Pluto if I can still call Pluto a planet. So if I call Pluto a planet here, I'd say, okay, this is maybe a good picture of it. But if you remember in that discussion, I said that if you looked at the angular momentum of Pluto, you would have an R, an M, and a V. But maybe a couple weeks later, or in case of Pluto, this would probably be months or even years later before it moved that far in the orbit. But when it's now over here, doesn't it have a different R? Doesn't it have a different angle, phi? Doesn't it even have a different velocity, v? But does it have the same angular momentum? And I made a comment that yes, it does, but it was a little premature to say that, but now I can say it with certainty. Why would I say that even though the R changes, and even though the phi changes, and even though the V changes, how do I know it still has the same angular momentum? Yeah, momentum is conserved as long as the net torque is zero. How do I know the net torque is zero? Is there an outside torque? Is there an outside force? Yeah, if you look at just the force of Pluto, I mean just Pluto, sorry, not the force of Pluto, but just Pluto by itself. And maybe I'll draw a little dotted line around Pluto. There is something pulling on Pluto. What is it? Yeah, in this picture it's the sun, and obviously in a whole solar system there'd be other planets. But ignoring the other planets here for a moment, we have the sun clearly pulling on it. So would you say that the linear momentum is conserved? No. And that's why the velocity changed. And the velocity did change, and now we have a new linear momentum to the planet Pluto. But is it possible to have a force and yet still have no torque? Yes, right, and we did that a lot in Chapter 10, and this is where it shows up again, is it is very possible, and you do have that in this situation. You have that in this situation because the direction of the force is straight towards the sun. So when you go to calculate the torque, you have this R cross F. And of course, whatever F is great, but you still have an angle of 180 degrees between those, and you end up with a zero. And so here's a situation where you have conservation of angular momentum, but not conservation of linear momentum. And that shows up in some of the examples and some of the problems that I want you to see today. So I'm going to jump on that and realize, okay, remember our three conservational principles? I mean, that's really what this chapter and this semester is all about. Learning Newton's three laws of motion and the three conservational principles. And I claim if you know those and you know those well, you can describe any motion that is put before you. Okay? And when we get to these conservational principles, we should ask, when is energy conserved? When is linear momentum conserved? And when is angular momentum conserved? And the answer was very simple. Energy was always conserved, although we may have added some from an outside source. So we had that extra term that, hey, you do something, pushing on it, you can add energy or take energy away from it. So we had to look at if there was work being done on it or not, okay? Same thing with momentum. Linear momentum, is it conserved? Well, I'll say yes and no. I mean, yes, it's conserved as long as there's no outside forces. But if there's outside forces, then the answer is no. So we got to look, is there a net outside force? Of course, if there is, we could always then incorporate that object into our system and end up with a system that has conservation of momentum. So that's why I said both yes and no, but it's really a question of look at the forces. Outside forces mean linear momentum is not conserved. And again, this is a good example of that going around in a circle. There is a force from the sun, and linear momentum will not be conserved. This falling pin has an outside force from the Earth. Again, linear momentum would not be conserved. Now, if I included the Earth, then I would say it would be. If I included the Sun with Pluto, then I would say it would be. So it depends on how I set up my system, and I can always set it up so that the momentum is conserved, but we got to be careful with that as we go to apply our conservation of linear momentum. And the same thing is true about an angular momentum. We've got to be careful on how we apply it. But if there are external torques, then we would say no, angular momentum is not conserved. And if there are no torques, then we would say yes, it is conserved. And so I wanted to make sure I emphasized that. I even know we kind of touched on it on the surface, and maybe even touched more so on the linear one. But that's a big step as we go into the examples here today. So here we go. We did number 25. Like I said, I even gave you a hint towards number 36. I'm going to come back to that one. But let's do 37 and 50 before we come back to the hint, because it will be very helpful, I think, as you answer these questions. So, I'm in the wrong chapter. But number 37 says this. A wooden block of mass capital M is resting on a frictionless horizontal surface and is attached to a rigid rod of length little l and of negligible mass. The rod can pivot around the other end, and a bullet of mass little m is traveling parallel to the horizontal surface and perpendicular to the rod with a speed v. It hits the block and becomes embedded in it. A, what is the angular momentum of the block bullet system? And B, what fraction of the original kinetic energy is converted into heat energy during the collision? Okay, so I just wanted to read it all the way through so you kind of got the bigger picture, and wanted to keep emphasizing that that's what you should always do, read it through, kind of get the gist of the problem. And in your case, now that you're learning so much, that kind of gives you a chance to stop and say, what principle is going to be important here? Is Newton's laws? Is it kinematics with constant acceleration? Is it conservation of linear momentum? Is it conservation of angular momentum? Is it conservation of energy? I mean, which one or ones of principles do I need to solve this? And so, setting this up, it'll hopefully come to me which one I need here. It says a wooden block of mass capital M. All right, so this is going to be my wooden block, mass capital M. Is resting on a frictionless horizontal surface. So since I'm drawing it on the whiteboard, let's pretend we're at the ceiling looking down. This is the top of the horizontal surface. Okay, so I got this wood block sitting on this white table, and you're at the ceiling looking down. So it's an aerial view, a top view looking down here. Let's see, frictionless horizontal surface, and it's attached to a rigid rod of length L. Okay, so it's got some kind of rod here of length little l. And rigid meaning it can't stretch or can't compress. It's always going to keep that same length. Okay. And of negligible mass. Okay, so in this one, they're going to say, don't worry about the mass of the rod itself. That'll change in the next one. That's going to be the difference between this problem and the next problem. Okay, but in this one, the rod's really light. It says the rod can pivot around its other end. Okay, so one end is connected here. So the other end right here kind of has a bolt or a screw or, some kind of hook there that it can now rotate around. So in other words, as we look down, this thing can spin, right? And so the block can move in a circle. And it's rigid, so the block can't move in an ellipse, and the block can't move out, and it can't move in a straight line. It can only move in a circle, a rigid object, pivoting around the end of the rod. Of course, I hear that end of the rod, and I think about the moment of inertia of a rod. But they said the rod was negligible mass, so I'm not doubt if I'm going to need that. Okay, so a bullet of mass little m traveling perpendicular to the horizontal surface and also perpendicular to the rod. Okay, so how is it going to be perpendicular to the horizontal surface and perpendicular to the rod? Well, here's perpendicular to the rod, and then it would be, you know, elevated above the table here, so it's going to be like that. So here comes the bullet. Basically, it's shot at the block at 90 degrees, okay, to the rod. Mass m traveling parallel to the horizontal surface and perpendicular to the rod with a speed v. It hits the block and becomes embedded in it. First question, A. What is the angular momentum of the block bullet system? Okay, maybe I'll start by asking you the three questions. Is energy conserved? Is linear momentum conserved? Is angular momentum conserved? Does the initial energy equal final energy? Yeah, okay, I'd say yeah, that's good. Yep. No added work from the outside. You know, no little cable out here, nobody pushing on it, none of these external force stuff we did back in Chapter 8. Okay, so a quick review of Chapter 8. How about then into Chapter 9? Does the initial momentum equal the final momentum? Well, what I was trying to emphasize is make sure you stay focused on what your system is. I mean, if we look at just the bullet itself, do we have conservation of linear momentum of just the bullet? No. Why would you say no? Okay, there's a colliding, and by colliding you say there's an outside force on it, right? So anytime we have an outside force, we'd say no, its momentum would change. That's what this mathematical statement says. You have an outside force, you will change its momentum. All right, so if I'm going to use conservation of linear momentum, I can't just say the bullet, right? That's not going to work. Because as you pointed out, doesn't the bullet rub against the block? Okay, so that would lead me to think, well, why don't I include the block here? Now do I have conservation of linear momentum?
No.
Yes or no? So some of you say no, why?
Isn't it tension? Like once it starts swinging, that's an outside force in the x direction.
Tension from where? No, you're on the right track. So I don't want to discourage you, but I'm just trying to pinpoint this down. Because for those of you who say, no, you're right. Where is an external force coming from here? Forget gravity. Whoever said gravity. I'm ignoring gravity here. That's not the point of the problem. Far more important than that. What else is happening here? Where's the force coming from? Yeah, it's coming from the fact that you have an axis right here, right? This thing is bolted in. And so whatever this thing is made out of, say it's a nail, right? And it's made out of the steel of that nail. What ends up happening is right here that this thing does have a force. And in fact, you could probably kind of see what would probably take place during the impact. Is that during the impact, this is hitting it, pushing it that way. And you can imagine, what if this was not tied down? What would happen instead? Yeah, it would go like this. And then you would have conservation of linear momentum. Yeah. But as soon as you add this in here, there is a force through that axis. Just like we had done many times in Chapter 10. We said, look, doesn't the gearing and the ball bearings or whatever that axis, don't you have forces through there? And so we do have a force here. So I would say, again, even if we include the bullet and the block, we still have an external force. So do we have conservation of linear momentum? No. Of course, now we can ask the question, well, you want to include, this is probably hooked to the Earth. So shall we include the Earth? Then I'd say, yes, we have conservation of linear momentum. But that's, I don't think the good road to go down, because then there's so many other things we don't know about it. And that's not even the question. The question kind of leads us down the road of looking at the bullet block system when they just ask the question, what is the angular momentum of the bullet block system? Okay? So at this point, you really didn't even have to ask these questions, but I wanted to make sure we asked it so that we would be ready for, any type of problem as we go to decide how to solve this. Which is conserved? Is energy conserved? Is linear momentum conserved? Is angular momentum conserved? So that leads me really to my third question, which is going to become important to answer question A. Does the initial angular momentum equal the final angular momentum? It's conserved if what? The net torque is 0. Do we have that? Yeah, and here too is an example. Do we have a force but no torque? Yeah, if you calculate everything around this axis. So please remember, when you go to calculate angular momentum, as we talked about, isn't it the angular momentum about, and then you have to say what point or what axis. And so the calculation for angular momentum is not just a simple number, it is about what axis. That was that long discussion we had near the end of class on Monday, that you can't just say, just like you can't say moment of inertia without saying what axis, So same thing here, is that if I pick this as my axis, the advantage of that is, even though I have a force, I have no torque. And with no torque, that means angular momentum is conserved. And that's what I want to keep in mind. And so as I prepare to solve this problem, I can use conservation of energy. I can use conservation of angular momentum. I cannot use conservation of linear momentum. So if I try to solve this problem with conservation of linear momentum, I will get a wrong answer. In fact, if I did both of these, I would get two different answers, and I would be stuck going, how come I have two? What's not working right here? Well, I'll tell you what's not working right is linear momentum is not conserved because you have an outside force. So we have an outside force but not an outside torque. So 2 out of the 3 are conserved. Okay? And so yes to energy, yes to angular momentum, but not to linear momentum. Which actually helps me out really well when I go to answer A. So as I read the question A again, it says, what is the angular momentum of the block bullet system? And kind of my first question is, well, are they talking about before the collision or after the collision? Which one do I do? Yeah, and the answer is it doesn't matter which one you do, right? Isn't the angular momentum the same as before and after? And so that's why I wanted to emphasize that. That's why the author doesn't even bother to say. He says, look, calculate the angular momentum of the block bullet system. And if you ask before or after, you're kind of missing the point that it doesn't matter whether you calculate it before or whether you calculate it after. Because whichever you do, it's the same. And that's why I wanted to go through this discussion. So that brings us what? How do you want to calculate it? Do you want to calculate it before the collision or do you want to calculate it after the collision? Which is going to be easier? Yeah, and I think before the collision. We've been doing that for the last couple problems. An object going in a straight line. That was that DMV that we got. I mean, well, let's do it again here. But if I go to calculate what is the angular momentum before, it would be R cross P. And so as I go to calculate this, noting that before the collision this one is not rotating at all, that's why I like to pick before the collision, because I know before the collision all the angular momentum comes from the bullet. None of it comes from this block, because this block being stationary. Of course, the thing to remind you of is, can you have angular momentum of an object going in a straight line? Yeah, so again, don't let that slip your mind. That was a long discussion we had on Monday, and that's why we had part 3 of that lab. Part 3 of that lab was really to show you that that ball moving in a straight line, just like this one, when it gets caught, does go in a circle. So a moving ball, although in a straight line, does have some angular momentum. In fact, you got a interesting homework problem with one that has a ball being dropped from a building, or I think it's the end of, anybody have done it yet? There's a flag post sticking out and a little knob on the end of the flag post falls off and it goes straight down. But the question asks about the angular momentum and how it changes as it goes straight down. And so the angular momentum does change because of gravity. But then you can calculate the torque and see how they do it. So you do a ball going in a straight line using torque and angular momentum. It's probably not the most efficient way to solve that problem, but it's one that emphasizes the principles of rotational motion and torque and angular momentum really well. So I picked it as a homework problem. But my point is that we can calculate this. And so if again I extend this out and call this R, and then this is mv, and this is some angle phi. When you go to calculate this, it would be the magnitude of the first one, r, magnitude of the second one, momentum is mv, and sine of the angle between them. And I guess technically, to make it a vector, it's got to have a direction. So this is the magnitude of the cross product. And then I can get my right hand out here and say, okay, there's R cross P, gives me into the board. And so the direction of the angular momentum is in the negative Z direction. And now I can look a little closer at, like we did before, the R and the phi, because where that ball is keeps changing R and phi, but it doesn't matter where the ball is, or not ball in this case, it was a ball in the lab, but in this case it's a bullet. It doesn't matter where the bullet is, you take R and you multiply by sine phi, you're always going to get this distance. And here's where I'm going to call that L. I think in my picture you might say, isn't that a little bit more than L? And I'd say, yeah, it probably is a little more than L. We just don't know how big that block is. We won't give it any dimensions. So my picture probably doesn't represent it as what the author intended. The author probably intends you to think of that as just a blob out at the end and all the mass is out an end. Or put another way, L is much bigger than the width of the block. Otherwise you'd probably have to give us some dimensions of the block. We'd have to say it's half the width of the block, and he doesn't do that yet. Those are some harder problems later on, but at this point we're just going to call it L. So this would be the angular momentum, and let me not forget my directional piece, but there is the initial angular momentum. The L, which when we did it we called it a D, and then the M and the V. So not a surprise, we come out with the same thing for the angular momentum. So dmv, or in this case lmmv. And so there is A. B is a little more mathematics here. Hopefully it's kind of the same physics. It says, okay, now what fraction of the original kinetic energy is converted into heat during the collision? So obviously during the collision there's some rubbing going on, and as this bullet gets lodged inside here, that rubbing turns into heat. And that's what they're asking for. They're asking for that number, kind of. Are they asking for Q? Are they asking for heat? Not really, right? You've got to be careful. Let's read it again. What do they ask for? What fraction? So what are they asking me to solve for?
The constant. U over the initial energy.
Yeah. So they're really asking that. So hopefully you kind of recognize that. Right? They're saying solve for the Q over the original kinetic energy. In other words, coming back here to this problem right here, we had already said earlier on that the energy is conserved. So what would happen? Well, I guess you would start with some original kinetic energy due to the bullet, right? So let's call that K sub I, original kinetic energy. Okay, and as that comes in and makes impact, where does that kinetic energy go? Okay, clearly some of it goes to heat, and maybe even quite a bit, I'm not sure. But all of it? No, because what else is going to happen? This thing's going to be rotating, so it's going to have a rotational kinetic energy. And so I would say 1/2 I omega squared goes there. And so that would be applying my principles of conservation of energy. And I can even write that as 1/2 m v squared.
For angular kinetic energy, you also write it with a K? There's no different symbol for
Oh, right, there is no different symbol. So if I left it as a K, I would just call it K final. But yeah, there's no symbol for a rotational kinetic energy versus a translational kinetic energy. Yeah. Okay, so keeping that in mind, now I can start to work on this. Okay? And so as you noticed over here, to get the Q would be, well, this is how much you started with in terms of kinetic energy. This is how much you ended with, and the difference between those is the heat. Okay? But again, we just want to emphasize the question. If you can miss that real easy. The question is not saying find Q. It's finding Q over the original kinetic energy. And in fact, I should probably put the original kinetic energy the original kinetic energy is a 1/2 mv squared. And that helps me with my algebra because the first term then becomes a 1 minus, and the halves cancel off, and you have I omega squared over mv squared. And so that's what we have so far, anyways.
And then there's the omega r over v.
Okay, well, okay. All right, so now you can say that the omega and the v's are got to be connected together, right? But your first one, you just said here, does omega equal v over r? Well, yes and no. I'm going to say no to this one. I mean, yes, this is the formula that connects an angular speed and a translational speed. So if this is the, what I'll call final angular speed, which sounds kind of funny because there was no initial angular speed here, okay? But if this is the angular speed it has after the collision, then it is related to the linear speed that the object has after the collision. But don't call that this v. That's my warning for you. Is the velocity of this object going around in a circle the same velocity that the bullet was coming in? No. And so if you went down the road of saying that is v over r, and you treated that v as the same as that v, you're going to run into troubles. That's not what those mean. So, does omega equal v over r? Yes, but this is the final speed and this is the initial speed, so don't cancel them off. Okay? So, is there a connection? Yes. And I don't think this is a good connection to go down, because I don't even know what the final speed is. Oh, but I can get it. How am I going to get it? Well, it really comes from this statement. Is it the initial angular momentum related to the initial speed? And is it the final angular momentum related to the final angular speed? So when we did A, we stopped right here. But if we went one more step, we could say LMV, which is the initial angular momentum, would equal I omega, right? That would be the next step in that line. There is a mathematical relationship between the omega and the v, of course. And so that's what makes B, I think, a hard problem to do, because we're going to do this. We're going to use conservation of energy, but we also have to incorporate conservation of angular momentum. And we better not use conservation of linear momentum. But once we see that, we can see there is an omega and a v here. In fact, let me solve it as in a ratio as omega over v. So that would become an L and M over I. And that will help me over here where I go 1 minus, and I will leave the I and the M alone here. And then I got my omega over v. And this says square it. So I've got to go L squared m squared I squared. And I still have a lot of algebra to do. So like I said, this is a much longer problem than it may have looked like on the surface, and certainly longer than the other two little examples we had done in this chapter, but not longer than most of the problems we will do in this chapter. So let me simplify this a little bit. This is 1 minus, and it looks like one of the i's upstairs will cancel and one of the m's downstairs cancel, and you're going to be left with an L squared m on the top and an I on the bottom.
Wait, how'd you get to that from there?
From here to here?
Yeah, from there to there.
Omega over V is LMI. LMI. So if you square it, omega squared over V squared is L squared, M squared, I squared. So I left the I and the M alone and did a substitution. I took this and substituted it right there, which is why that showed up right there. All right, so I'm getting closer. I still think there's more I could do and should do, because the author gave me things like L squared and M squared, and as we said, the general rule is put the answer in the variables that they gave you. So they gave me an M, they gave me an L, but they didn't give me an I. So let's go back to chapter 10 and figure out what the I is for this case. Right, so this we can think of as two chunks of objects, one the wood block and one the bullet. Fair enough? And each of those being a distance of L away from the rotational point. So this is probably the easiest I you can calculate, but still we got to calculate it. The first one being the bullet and the second one being the block. Each of them being a distance L away. So there would be the rotational inertia. And so now I have two terms, and so I'm going to get a common denominator. So this one becomes L squared plus M squared, and then I got the minus L squared M, which means the first one and that last one cancel off. So I've got an ML squared over an ML squared minus ML squared. Looks like there's an L squared in each term, and I get capital M, little m over big M. Yay, there it is. And so it took me a little while to get there, but amazingly simplified to something quite small. So total mass of the block divided by the total mass is the ratio that's converted into heat. And it's really the same number you saw when you did the momentum lab, not this week, but the week before when you shot that little cannonball.
What happened to the one?
Oh, the one is right here, and I got a common denominator.
Oh,
Minus. And so I put this is the one, yeah, and then this, yeah, like that. Yeah, so add two fractions, common denominator. And I know you didn't forget, you were just asking. But my 7th grader last night was reviewing for his math standardized California test scores, and and so Dad, I can't do these. Well, you did these last year. They're easy. Anyways, so didn't remember anything I said. When you add and subtract, you've got to get a common denominator. Oh yeah. So of course, then he goes to the next line, which is multiply, where you don't need a common, right? And he goes, oh, I got to find the common denominator. No, what did I say? No, I said if you add or subtract, you need a common denominator. If you multiply, you just multiply across. Yeah. So it was good that he had the review because he needs the review really bad. Was messing that all up. But anyway, that was good. Somebody else had a question. Did it get answered? Okay. Anyway, so like I said, after quite a bit of algebra, it amazingly simplifies a little bit. And I know there was a lot there. That's why let's do the next one, 50. You'll see kind of the same thing. Different shape, different dimensions, different eyes, but same logic. So let's do number 50. If that didn't make complete sense to you, maybe this next one will make it a little more sense to you. This one says, a projectile of mass m is moving to the right with a speed little v. The projectile strikes and sticks the end of a stationary rod of mass capital M and length d that can pivot about a frictionless axis through its center. All right. Let's see if we can put that much on the board. In fact, they even give a little picture here. They show the little particle of mass m moving with velocity v. So the same as before. The last time it was a bullet. This is a little particle. They don't even say what it's made out of. Maybe it's one of these little rubber, or maybe silly putty because it's going to stick here. So we throw this little rubberized piece, and it's traveling with some velocity v. It's got a mass of m, but they say then it is traveling towards the end of a rod, and it's going to stick to the end of that rod right there. But the rod can then rotate. So the rod has length d and can rotate around a fixed axis here. Okay, so projectile mass m moving to the right with a speed v. The projectile strikes and sticks to the end of a stationary, so they tell us it starts off not moving, stationary rod of mass capital M. I didn't put a capital M here, but the rod has mass capital M and length d that can pivot around a frictionless axis at its center. Okay, A. Find the angular speed of this system right after the collision, and then B, determine the fractional loss of energy during the collision. So we're back to that same question, the fractional loss of energy. But with A, before we even ask A, let's ask this. Is energy conserved? Is linear momentum conserved? Is angular momentum conserved? So let's start with the energy. Is energy conserved? Yeah, so there's no work being done by any outside sources. There's no energy being added or taken away from it. So the energy before equals energy after. So yeah, okay, that I can use that idea. How about linear momentum? Again, no, why not? There is some outside forces, right? There is, during this impact, there would be a force on between these two, but if you include the rod and the particle as your system, those equal and opposite forces would cancel off. But it's this one here that creates the problem, because there would be a force from something outside of the rod or the particle. It's coming from that axis. And it's because of that there is an outside force. And because of that outside force, there is no way that the momentum before should equal to afterwards. In fact, it should change according to this little equation. There is an outside force, so there should be a change in the linear momentum. So we would not want to apply conservation of linear momentum to this. How about angular momentum? It is conserved if we calculate the angular momentum about this axis, because once you pick this is your axis, then you ask about this outside force. This outside force provides no torque, and so the torque is zero, so there is a conservation of angular momentum. So do we have conservation of angular momentum? Yes. So this is very much like the one we just did, obviously. I picked the two together because I don't think you kind of get everything the first time through. You got to kind of see it again and again and again, which of course is why I lecture on it, and I do examples, and I assign you homework, and you do a lab, and you study it, and by the time you've done all those, you come in and ace the test, right? So you've seen it enough, but that's the idea. All right, so there's our conservation of angular momentum. In fact, let me ask you this. How would this problem be different if there was no axis there? Okay, first thing of all, yeah, you would have no outside forces, and would you have conservation of linear momentum? And how would the behavior of the collision look versus this axis being here and not being here? Right, and that's the important thing to realize. You can see how much role this axis plays here, because if there was no axis here and this thing hit it, boom, what would happen? It would rotate and translate. And so if this was a collision in outer space, we would have both a translational and a rotational effect, and we would have conservation of linear momentum along with conservation of angular momentum. But in this case, with that axis, we get a different behavior. We get a different behavior, and it doesn't translate, it just sits here and spins, and that is shown up in the math here. The math is different also, because we have no conservation of linear momentum.
Where would you put your axis for the rotational?
Well, I'll help you. I'll tell you what. Let me answer that in a few minutes. We're done with this problem. As we go back to 36, and I give you a hint, because I want to look at 36 again, and I'll ask you, where do you put the axis there? Okay, because you have one just like this on 36. All right, right. Deciding where the axis is a hard one. That's why I wanted to help you get started on that one. Okay, so anyways, this is the general background, and I think you caught it. Now we can answer A here. It says find the angular speed of the system right after the collision. And really they're back to this A here. What would be the angular momentum right before the collision? Yeah, and do I have to do it again to calculate an object going in a straight line? No? Good? So what is it? Okay, good. You did notice it's d over 2 mv. How come it's not d mv like it's been in the last time? Yeah, because the way we label d is different. It's still the distance away, and so this is the perpendicular distance away. It's just that we labeled the whole rod as d. So if you caught that, which looks like you all did, yeah, it's really the same formula, that LMV that we had in the last problem, or the DMV that we had in the lab. It's just our L or our D is represented with this distance, which is now half the length of the rod. So that's the angular momentum before the collision. And of course, then it sticks to it and starts to spin. What would be the angular momentum there? Well, I'll just write it as I omega, because it would be whatever the rotational inertia is, and it's spinning there at some angular speed. And that will help me answer the question, because the question says find the angular speed. And so when I move I to the other side of the equation, I can simplify it a little bit. The numerator becomes dmv, and the denominator becomes 2 times I. And I probably shouldn't stop there. Again, same logic is that you should give answers in the same symbols that they were given to you. So clearly they gave me the particle of mass m moving with a velocity v, a rod of length d, but they didn't give me the I. But they did give me the m of the rod. So I probably need to go back and figure out what is the moment of inertia of my system, and then I will be done. All right, so I'll leave the numerator alone, dmv. How am I going to get I of my system? Yeah, and hopefully you see it's 2 things added together, right? It is the rod and that little blob. Let's start with the rod. How do you get the moment of inertia of a rod about its center? 1/12. So that's 1/12. Then it's the mass of the rod, which in our problem they're calling capital M, times the length squared of the rod, which in our case is the d. So there would be the moment of inertia component for the rod. And how about the blob now sitting at the end of it? Okay, it's just mr squared, so it's m, and then what's r? Yeah, and so d over 2 squared, right? And so there's the calculation for the moment of inertia. All right, now I suppose I should do a little simplifying here, because that is a compound fraction, if you will. What do I want to do first? Why don't I... Well, will it be okay if I write the first one like this with a 12? The next one is an md squared. Now it's over 4, isn't it? But would it be okay if instead of me putting a 4, I'll multiply it by top and bottom by 3, so I get a common denominator? Okay, so it's 3/12, that's 1/4. Okay. And of course now I can begin to factor a few things. Here's a D, here's an M, here's a V. And I'll leave the 2 alone for just a second, but making the 12, I can either add them, or in this case I'll just bring out the 12 first. But there's also a D squared. So a D squared and a 1/12 are there. So that leaves this one with an M, and that leaves this one with a 3 times a little m. And then I can reduce a little bit. That's a 6. One of the D's cancels off. And so in the numerator I have the MV. The 6 goes up to here. The D, the capital M, plus the 3 little m. And maybe that's the best place to stop. I think we've answered the question of, did we write it in the terms that were given to us? The M, yes, the V's, the big M and the little m, yeah. So there is the answer to the question of what would be the angular speed after the collision based upon the information given here. So there's my A. And the same question for B that we had before. Question for B then is what fraction is lost, or what remains. I think this one maybe asked it a little different. What did it say? 50B says determine the fractional loss. Okay, so it is heat. Fractional loss of energy due to the collision. So again, they're still asking the same thing. They're saying how much heat compared to what you start with. Okay. Now again, to answer the heat question, we can come over here and say, well, there is an original kinetic energy, and there's going to be a little bit of final plus any heat that's created. And I'm going to use your idea of, hey, why don't we just call that final kinetic energy, which of course comes from the rotational one, so we'll add that to it. But what it means then is kinetic initial minus final kinetic is the heat, and then I divide that by the original. So this becomes 1 minus final kinetic over initial kinetic. And so same thing as we had in the last problem, written a little bit different because we wrote it as the final as 1/2 I omega squared, and the initial as 1/2 m v squared. And then we canceled off the 1/2. And so at some point, although we got here with different symbols, we got to the same equation that we had before. And so this step is just like before, whereas I can pause here and say, do I know the relationship between the angular speed and the linear speed? And the answer is yes, I do. That's what this line was all about here, right? Or we could even go back to this line. It all depends if you want to include the I or not. And why don't we do it this way? just because it still has an I in it, and then it's going to cancel with that I, although not completely. So we're still going to have to calculate I again. But maybe, like I said, I'll just write this then as omega over V here is equal to an md in the numerator and a 2I in the denominator. So if I were to square everything, that's what I want to put over here. So this is 1 minus, and I'll leave the I and the m alone, but the omega squared over v squared is an m squared and a d squared and a 2 squared, which I'm just going to write as a 4, and an I squared. And then we can cancel a few things. We can cancel one of the i's, and we can cancel one of the m's. So it's 1 minus, and in the top we have md squared, and in the bottom we have the 4I. And now we can do what we did in part A, is we don't want to leave it with an I in there because, again, they didn't give that as part of the problem. They gave masses and distances. So I need to do this. I need to go, well, how did we calculate I? And we calculated I by saying it is a rod about its center, 1/12 md squared, and a small blob of mass m, half the distance of the rod out. And so maybe I should give myself some more room. 1 minus, I've got the md squared there, and here's the 4, and as we did before, why don't I write that over 12? This is the md squared here, and then this is 3 md squared there. So 1 minus, and I've got an md squared, and I can factor out a 12 and a d squared like we did before. So if I factor out a d squared and a 12, I get an m. If I factor out a 12 and a d squared, I get a 3m. And of course, what's nice about this is this reduces a little bit to a 3, and the d squareds cancel off. And so I'm left with a 3m in the numerator, that 3 with that m, and then a capital M minus a 3m. Now I'll do my common denominator. All right. I was trying to be nice to you. Don't want to be caught on videotape killing a bug here, but it might happen. All right, so if I then put a common denominator here, then I reduces to, and so again, I think quite surprising to me anyways. That's how much it reduces. After all that work, I can find the fraction. And so there's the fractional loss of energy. So between using the principles of conservation of angular momentum and conservation of energy and a lot of algebra, getting a common denominator, I get the answer. Now, like I said, that was a lot of time and a lot of work. But I think it sets you in a perfect position to, one of the challenging ones in this chapter, which I wanted to give you a hint towards as you are doing the homework here, is this number 36. So let's put that one on the board again. I gave a kind of hint towards it real quickly, and really couldn't do it justice because I hadn't spent enough time talking about it. And so let's look at this one again. Here's this one, and it describes it this way. It's got a smaller puck of mass. Ooh, let me just call it little m. But they don't even call it little m. They give the density. with the idea that the bigger puck is going to have more m, but the same density. So given the size of the pucks, you can get the ratio of the masses. And so that is part of that in there too. And I'll just throw that hint out there. But that's not really the main part of my hint. The main part of my hint here is when these two come together, the problem says that on these edges right here, there is a Velcro or something that makes them stick. And what does it say? Glides across the table, speed 1.5, a glancing collision with the second, such that the rims just touch. Because the rims are coated with, instant acting glue. There we go. All right, so it's not Velcro, it's instant acting glue. All right, but they stick together instantly. And what happens next is my question for you. Yeah. And so what will happen is without that axis that we were talking about, and I asked this question, is linear momentum conserved? The answer is, this time, yes. Is angular momentum conserved? Well, yes. If there's no forces, both of them are conserved, because there's no way you can have a torque without a force there. All right, so what ends up happening, as we were discussing, is this one comes in, and when they stick, it rotates and translates. So I've got to use both of those principles. And here to answer your question, I'll get to your question, is you're going to ask, well, what axis? Because every time I go to calculate an angular momentum, I have to pick an axis, okay? Fair enough. But I would say this. The real key to the problem is you have to be consistent with that axis. So when it's tumbling, aren't you going to want to know its rotational speed around its center of mass? So I would say you're going to want to calculate its angular momentum around its center of mass here. So do the same thing here, which the center of mass is a little bit, inside of the bigger one. It's something. Well, now you have to go back to chapter 9 and do a center of mass calculation, right? I mean, figure out where this center of mass is, which is, like I said, why I think it's a hard problem here, which is why you've got to know the size of this compared to the size of this, so you know how much bigger this mass is compared to that. And they give you that information in the problem. Obviously, I'm not doing the whole problem, but I'm trying to help you here, saying they give you enough information here that you can find out where that center of mass is. Find it, okay? And maybe even think about it right before they contact. And so when you find the center of mass, you will, of course, discover that it is not at the contact point. And I think if you look at this before the collision, you're very tempted to calculate the angular momentum either from the center of this one, or maybe the center of this one, or maybe the contact point, but not necessarily at the center of mass. And so that's really what my hint is about. Since you're going to probably calculate the angular momentum around its center of mass after the collision, do it before the collision also. You can't just change your axis in the middle. So remember, it's conservation of angular momentum. And the angular momentum depends what axis. So pick an axis and you got to stick to it. And it's like I said, if you're going to do this one for a rotation after the collision, you need to do that axis before the collision.
So what do we need to know the center of mass? You need two center of masses on the before the collision.
Well, what I drew was the center of mass is moving because the objects are moving. So the center of mass would be, say, here. Then as it gets closer, it'd be here. When it gets here, it's here. And then right before they make contact, it's here. So I wouldn't mess with that one. I would mess. And so that's your center of mass. And so when you go to calculate the angular momentum of this one moving, this is your D in your DMV for calculating the angular momentum. Your D is not the radius of either of these pucks. It is that distance of the center of mass. And that's the tricky thing to catch. Okay. And And of course, they also ask here, A, what is the angular momentum of the system? Oh, this new version actually helps you out a little bit. That's good. You don't even need the hint, because the A does say, calculate the angular momentum of the system relative to its center of mass. So they helped you out, because it used to just be the B only, where it would say, what is the angular speed after the collision? You know, and so to do that, people would do one axis, one origin here, and another origin here, and come up with funny numbers. Yeah.
So you have to make your origin
Yeah, yeah. But by them asking it that way, find the angular momentum relative to the center of mass, that's going to be making you find center of mass first and then calculating it relative to the center of mass. So that's a big help. Almost too much. Now it's an easy problem. I don't even need to give hints anymore. I'm going to stop giving for that one. All right. Well, hopefully those made sense. Now that we've done the easy ones, shall we do some hard ones? And I do think these are a little bit harder, but if those other ones kind of made sense, then we're just going to take one more notch up the ladder. And so hopefully you won't think this is a harder one. You'll just think it's the next logical step here. But it's got a lot of pieces to it. And I think really at this point in the class, that's what kind of makes these problems hard. It's not just that it's kind of new material and it's rotation, which I think rotation is harder than translation, but I think it's also the fact there's so many details to keep track of by now. Where you're looking at the linear motion and the rotational motion, and then what axis is it rotating around? How do you calculate the moment of inertia? And so you got to go back to all these chapters. How do you calculate the center of mass? And you got to go back to all those other little pieces of the puzzle. And this is a good illustration of that. Listen to this one. This one says you have a solid cube of wood of sides 2a and of mass m, and it is resting on a horizontal surface. So I'll pause right there and just draw the picture as they have in the book. They say, okay, here is a cube. And I'll try to draw it in 3 dimensions here. So here's my cube sitting on some kind of table or something. Okay, it's solid wood. They even help label it by saying, let's call this corner A, and this corner back here B, this corner up here C, and this one towards the front but up high D. They say the dimensions of it are 2A by 2A by 2A. Actually, they just say the sides are A, but it's a cube also, so make sure you caught that. They're saying it's 2A by 2A by 2A. All right? Maybe I'll get that out of the way by putting the dimensions back there. So it's 2A. But here's where the problem begins here. They say, all right, the cube is constrained to rotate around the axis AB. All right, so AB, this edge of the cube. I should have brought a cube. Maybe I'll let the book's not exactly a cube, but here is the cube, and then this is AB. And then what they mean by constrained to rotate is maybe there's some kind of tape laid across here, duct tape, or a hinge. So what it can do is it can rotate, but it can't translate. In other words, right here, there is a hinge that you might find on the door over here. A couple of screws and a hinge. Maybe another one here. Something like that. So the block can rotate 90 degrees or back, but it's bolted in, so it can't slide. Okay? And so again, remember that first step, a good physical understanding and a good physical picture of what's going on. Otherwise, you might go down the wrong roads. And that's what it says. here. A cube is constrained to rotate about the fixed axis AB. Now, a bullet of mass little m and of speed v is shot from the opposite face of ABCD. All right, so the opposite face of ABCD is over here somewhere. And so here comes this bullet of mass m traveling with velocity v, shot at this block. So there's our collision. It is shot at a height of 4/3 a. So this bullet is going to strike at a height of 4/3 a. So in other words, it's more than halfway up. And that's important here. Because as you hit it more than halfway up, what begins to happen? It begins to rotate. So it can rotate, or it will rotate. It says here that the bullet becomes embedded in the block. Find the minimum speed v of the bullet needed to tip the block over onto the face A, B, C, D. So I'm hoping you kind of see what would happen. If this was a bullet that was fired really fast, it would hit here and turn it over, right? And if it was really, really slow, what would happen? Yeah, it would kind of hit the block and it would go boom, boom, right? And it wouldn't be enough to tip it over. So what they're asking for is just enough speed that it gets it how? Up. And then gravity takes it the rest. Okay? And that's an important concept right there. If we're going to write out these equations, we really need to realize that you don't have to shoot the bullet hard enough to make it go all the way over. You just have to shoot the bullet hard enough to make it go up to where? Yeah, if you... Oh, well, maybe I better do 2 dimensions first. Oop, that's a terrible square. All right, but if you get the block kind of in that position, okay, I get it in this position as it goes over. All I got to do is get its center of mass right there above the axis. And then gravity will take it the other way, right? Or maybe just a hair more, because if it's right there, you know, it might tumble either way. But let's figure out what speed is needed to get it right there, at center of mass. Okay? And so when I get the center of mass to that position, then gravity can take care of the rest. Anything faster than that, we'll put it over. Anything less than that, we'll not quite put it over. Okay? And so that's kind of the logic in this step. Fire this bolt, get it lodged inside, tip it to this point. So how do I do that? Well, do I have conservation of linear momentum? Do I have conservation of angular momentum? Do I have conservation of energy? And so ask those 3 questions first and say, well, let's see. And hopefully this looks a lot like the other 2, not the one we just did, the 36, where we had conservation of linear momentum. But the other ones before that, we had a hinge and we had something that would supply the force. And so right here, down at the hinge here, this axis AB, there is a force. When this comes in, this pushes back. There is an external force due to those hinges. Therefore, we do not have conservation of linear momentum. But we do have conservation of energy, and we do have conservation of angular momentum, We just do not have conservation of linear momentum. Fair enough? And again, this will hopefully be enough information to solve this question about what speed does it have to travel in order to just tip it over here. Okay? And maybe I will start here with the energy. The bullet's coming in, so I would say it starts with an energy of 1/2 mv squared. Now it makes impact. And obviously during the impact, there's a lot of rubbing going on. The bullet slows down, the block speeds up, a lot of heat is created in there, and at that point, the system will be rotating a little bit, and that's what's going to start lifting it up. Okay? And then, of course, it has some heat. Okay? And that's just the impact. Because now, what begins to happen as it begins to rotate? Where does this go? Where does the 1/2 I omega squared go? Right, into a potential energy. And if we're going to say it's just enough energy to get it up to the top here, then we have an mgy final. Now I did something in here that hopefully was pretty obvious. Did I give it any potential energy over here? Why not? Okay, see, so I'm actually setting my axis at 0 somewhere, right? When you say there's no potential energy, you're saying because its height is 0, right? All right, so indirectly, I have chosen the axis. I didn't even pause to ask you. Maybe I should have. But where is the axis then? Where, yeah, the center of mass. Where's the center of mass? Isn't this height A? Right? Isn't that where I am setting y equal to 0? And so maybe I should even backtrack a little further. Do you not want to call that y equal to 0? I mean, I'm happy to call somewhere else. Remember, we can choose it. Where would you like to pick y equal to 0? You good with that, or you want me to call the table? I mean, I don't care. But it is going to matter because I got to say how high does it go. And to say how high it goes, you got to measure it from 0. So pick the 0 and use it.
Isn't the center of mass after the collision going to change since the bullet is embedding itself?
Oh, fair enough. Fair enough. I don't know if I verbally said this. And of course, then it would also depend where the bullet is embedded. But they do say this statement here, and I don't know if I read it this far. Let's see, it says, the bullet becomes embedded in the cube. Find the minimum value V required to tip the cube so that it falls on the face A, B, C, D. Also, assume that the mass of the bullet is much, much smaller than the mass of the cube. So, I should have added all that. So we're going to say the center mass doesn't change. Yeah. Otherwise, we would need to know where it stopped inside there, and then it's certainly a much harder problem. So, yeah, good question, good point. All right, now, if you're willing to then take y equals to 0, see, this is what I said, where did we learn all this energy stuff? Wasn't that chapter 8? Ooh, center of mass, chapter 9. Rotation, inertia, chapter 10. Angular momentum, chapter 11. So this problem just took chapters 8, 9, 10, and 11 and put them all together. And we're not even done yet. Yeah?
Could you explain to me how you know those are equal? How do you know it's equal to energy?
Here? Yeah. This is a second conservational energy statement. If I have something that, and maybe I'll get away from rotation and just go to translation. If I am throwing this up, right here, it has a certain kinetic energy. Where does it go? Into potential energy. The reason it goes as high as it does is based upon how much kinetic energy here. So the kinetic energy, it starts down here. By the time it stops, has no more kinetic, and it's all potential. And so that's how we would have done it in chapter 8. Now, granted, this is rotation. So if you have something that's rotating, and so I have something like this, and I give it a little kinetic energy, and I ask how high does it rotate up, when it gets to here, you know it has come to a stop. So where does all that kinetic energy go? Into potential energy. So I take the kinetic energy that I have immediately after the impact, so that's what I meant in this statement, that the kinetic energy it has immediately after the impact, so there's the kinetic energy immediately after the impact, then makes the block go higher, and as it goes higher, it's losing its kinetic energy and then gaining potential energy. So that's the energy immediately after, kinetic energy immediately after, and then the potential energy when it gets to its peak. Whereas this is the kinetic energy immediately before the impact, kinetic energy immediately after, and the heat that's created during the impact. Okay. All right, so let me finish this line here. So this is the kinetic energy immediately after the impact. This then would be the mass, and I put a little m. That was probably poor timing on my part because I just meant in general m, but your author had used little m here for this bullet, and I don't mean that. I mean the mass of the object going up, and in this case it's the capital M. It's the block as it rotates over. So let me change that to a capital M. But here's what I was really after. How high does it go? Okay, good. So you guys are comparing this picture where the center of mass is A above the table, to this picture, which the center of mass is how far? Okay, so if I make a triangle here, this is A, this would be the hypotenuse, so this would be root 2A, right? So the height is root 2A minus A. That's how much higher it went. Fair enough? Because it went up from there to there. Which kind of makes me think maybe I should have just measured everything from the table, because I'm doing that now to tell you how to figure out how high it is, right? Because I want to measure it how high it goes up from A. That's where I'm going to call y equals 0, at A. So how high is it above that? So it goes up to root 2 over A from the table, but I want to know how much it goes up from my reference point, so I subtract the A. Okay, so there is the first step of this, conservation of energy. But don't I also have conservation of angular momentum? All right, so let's apply that. First question, like anyone when it comes to angular momentum, calculated about what axis? Well, we really don't have much of a choice. What is that axis going to have to be? Is it center of mass, or is it AB? It's got to be AB, right? Because AB is where the force is. And in order to have zero torque, you have to have the force at the axis. So conserving angular momentum is only going to work when you have zero torque. And the only way you get that is if you do it around AB. So this is a problem with doing the axis AB, not the center of mass as was done over here in 36. So again, that logic is what is needed, that fundamental principle, the stuff behind it that allows you to do these calculations. It's why You'll find it more true now than you ever did at the very beginning. I said, look, if all you do in this class is blindly plug and chug, and you think a bunch of formulas are going to get you through, you're going to run into troubles. There's sound, logical reasons behind all of these, and you need to know those so that you can do something new, something that hasn't done before. You need to know why the things are done the way they are. And if you don't get that, then it just becomes like this black box engineering stuff where you're just going to blindly plug and chug. And the truth is, you could probably look at an equation and go, it says mass and there's a little m in the formula, okay. It says velocity, and you know, it's my joke I was saying earlier, you'll do okay. And you'll get an okay grade. And you'll transfer to an okay school. And you'll have an okay career with an okay salary. Meet an okay spouse. And have okay kids, you know. But it's much richer than that. There's the difference between surviving and thriving. And I want you to thrive here. And there's a fundamental process involved. And physics is about that. You know, I keep saying, physics is about just knowing a few but powerful fundamental concepts that explain the universe here. And that's what we're trying to see here. All right, so that answers our question, that if I'm going to calculate the angular momentum, I need to know about what axis. What axis? I don't have a choice. It's got to be AB, because AB is the only axis that gives me zero torque. All right, so knowing that I've got to calculate it here, then I would ask this first question then, what is the initial angular momentum? What is the angular momentum of this bullet as measured from the axis AB? Yeah, and we've been writing it as dmv for the longest time. I'll leave the mv, but in this case, what's d? Yeah, it's the 4/3 a. Right? And so there is the angular momentum before the collision. What is it after the collision? Well, it would be I omega, right? Where I would be the rotation of this big cube tilting over. Which brings up a whole nother question I haven't even got to, but it's really chapter 10. What is the rotational inertia of a big old cube? Oh, well, let's hold off on that one. But nonetheless, that's what this is saying to me. And so I will work on that later. But it's going to be part of the puzzle here in order to solve this. So here is the relationship between the speed of the bullet and the angular speed after the impact. And that angular speed shows up here is what I need in order to make it go that high. So why don't I do that? Why don't I solve this for omega and put it into here? Because then I'm saying how much V do I need in order to get this much height out of my block, right? And so those are the two things being put together. So I will write this as omega is 4AMV, 3I. I will take that and put it over to here. And so 1/2 I, and then I will go omega squared. So I need to square everything. Square, 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 square. All right. So this is a 16 for the 4 squared. This is an A squared. This is an M squared. This is a V squared. This is then a 9, and then I squared equals mg. And if you don't mind, I'll factor out the A. Root 2, should I leave it as root 2 minus 1? Root 2 minus 1, why not? Tempted to just put 0.414, I mean that's in a decimal form, but I'll leave it that way so you'll see it in your notes where it came from. And so now I can solve for V, yay, there it is, right? Solve for V. Looks like I got a little bit of work to do though. It looks like this I cancels with that I. It looks like that 2 will cancel with that 16. And the way it stands now then, oh, and then there's an A on one side which would cancel with an A on that side. The m's are different, so I can't do anything there. But it looks like right now I've got an 8a m squared v squared over 9I equals mg root 2 minus 1. Okay. Should I solve for v squared first before I worry about the I? Why not? 2I g root 2 minus 1 over 8a m squared. All right. Now we focus on the I. What is the rotational inertia of a cube? Well, we haven't done a cube. Fortunately, your author put a bunch of rods together and made a plate for you. So maybe I'll start there with the plate. I'm going to skip back over here to chapter 10 and write this on the board. Your author has, okay, let's look at a rectangular plate. He says this: if you take a rectangular plate and you rotate it around its center, and the plate has dimensions A, B, he says that the rotational inertia around its center of mass is 1/12. There's the 1/12, doesn't surprise you, hopefully. A squared plus B squared, because the plate is the sum of a bunch of rods added together. But in the interest of time, I better not go all the way back to the rod, but we did the rod. And you add the rod, you get a plate. Now, a plate doesn't quite make a cube, so I'm going to have to go a little bit further from this. First of all, if you are talking about a cube, wouldn't you be taking slices of plates? And so in here, I could say this is a plate, and another plate, and another plate, and another plate, and we can add a bunch of plates together. Well, what makes it a little easier here is a plate that is part of a square means that A and B are the same. Fair enough? So I don't need to have both an A and a B. I can write this as 2A squared. Fair enough? Now, the other thing, though, I want to be real careful with, that's why I say this is a good problem. It's got a lot of pieces to it. I mean, this problem should take, 17 hours or something. All right? Is look carefully here at this. They said the size of my plate is 2A. But what do I mean over here by this A? Right. So be careful when you're comparing this, right? This really needs to be written as 2A squared. If I'm going to use the same A that we're talking about over here, and the same A I'm talking about over here. These are different A's. Okay, this A is the size of the plate. And the size of the plate, according to this, is 2A. Got to throw that in just to confuse you a little bit there. All right, so if you've got all that, then what you really have is a 2 squared. That's a 4 times 2, that's 8. So that's 8/12 MA squared, which of course reduces to 2/3 MA squared. So there is a plate. I don't even have a cube yet. Fortunately, this won't be a hard step. How am I going to go from a plate to a cube? Yeah, I'm going to add up a bunch of plates, right? And so you might say, all right, well, the I of the cube is nothing more than the sum of the I's of a bunch of plates. All right. I think your author uses the word sheet. No, he doesn't use plate. Okay, rectangular plate. All right, so I got this plate. All right, so let me add a bunch of plates together. Now, one thing that's going to make this nice is, aren't all the plates the same dimensions? All right, so if you look carefully at this, you've got to add up all these plates, you've got 2/3 ma squared. What's nice is that every plate has the same dimensions, and so we can pull the a out. And of course, what makes it nice is this is the sum of what? The mass. What was this mass? And wasn't this the mass of a plate? Isn't that where this came from? So this is saying the sum of all the plates. Now if you add up the sum of all the plates, what do you get? The total mass of the cube. So this would just come out to be 2/3 a squared mass of the cube. Okay. So good. How did they state it? I didn't put it up here in the drawing, but yes, we do want to give an answer in terms of the variables that they gave us, and I think they did say capital M. A solid cube of wood of size 2a and of mass capital M. So they gave us the capital M. So this capital M is the same as that M. So remember, these M's are the plates. Now maybe I better not call them little m's, because little m is the bullet. A lot of little pieces that can get confused. And so we're back to this. Make sure you're reading the math as you go along. You can't just do the math, okay? Doing the math only gets you so far. The blind plug and chug, the blind, engineering in a box, it only goes so far. Okay, the bigger picture of what is the whole picture. The more you can get the whole picture, the better. Now, I got to admit, some problems are so complicated. Nobody expects one person to design a whole space shuttle, so there is a little bit of, okay, I got to trust that team over there, that what they're telling me is true, and I'll go from there. But the more you have of the picture of going on, the more you can go from surviving to thriving and try something new and get that piece. Okay. But again, notice that, look at the pieces that I've put. Angular momentum from chapter 11, moments of inertia from chapter 10, energy from chapter 8, center of masses from chapter 9. And so I'm putting all these pieces together. Like I said, that's why I made a good problem with a lot of pieces. All right, so shouldn't I just take this then and put it over here and I'm done? Ah, good, you see it. I'm not done. What have I just solved for? After all this work, getting the moment of inertia. I got the moment of inertia of a cube about its center. What do I want? About the axis AB. All right, let's keep going. How do I get it around the axis AB? Parallel axis theorem, right. So I need to take this number, which is 2/3 a squared m of the cube, and add to it md squared equals 2/3, and I'm just going to put ma squared in that order, times m. And what's d now? Yeah, I'm going from the center over to this corner. How far is that? Root 2a squared. All right, so this is 2/3 ma squared plus 2ma squared, which if I get a common denominator, multiply by 3, then common denominator is a 3, a 2 and a 6 make an 8 ma squared. Okay, there is what I want. The rotational inertia of a cube about the axis AB is what was meant right there. All right, so I'll put it in. So here's the 9, the 8, the A, the M squared. And now I got this I, which is 8/3 M A squared. Right? 8/3 M A squared. And then I got the M, and then I've got the G, then I got the root 2 minus 1. Whew. All right, now, the 8 cancels with the 8. Yay! The 3 cancels a little bit, and I've got that. The A cancels with that A. Anything else? I think that's it, right? So there's the 3. There's the capital M squared. There's an A. There's a G. There's an M squared. There is a root 2 minus 1. Now, hopefully I haven't made any mistakes. It was a lot of work. But, oh, okay, yeah, and then that's V squared. So taking the square root of all of that would be the speed needed. And you would have never guessed that as the formula, I'm sure. Looking at all that, going, hey, that's the speed that I need. Of course not. That was the whole idea, is use the fundamental principles. The fundamental principles aren't that tough, and then they end up with a whole system of equations, and you have to solve them and work them out, and a lot of details here. And that's why I joked, how long did this take? Half hour? And I said, all right, want to do a hard one? Here's a hard one. And that's not even magenta. Shall we do a magenta one? All right, let's do a magenta one. We got 2 magenta ones. We only got 15 minutes left. We'll do our best here. But I think that's enough time, because the ones are magenta, not because there's so much math or so much detail from other chapters, but just because getting a good physical connection to this is really kind of the tough stuff here. And the 2 problems are actually tied together. So once you do the first one, you're 3/4 done with the second one. And so that's why I thought, these will be a good ones to group together. But they really help with, I think, the understanding of the 2 things going on that I'm trying to relate to you. Is you got to look at translational motion, and you have to look at rotational motion. And you got to solve and set it up accordingly. Here's the problem. Number-wise, it's number 58. So I'll put number 58 here. I'll also put 59, because hopefully we'll have enough time here to do not only 58, but 59. And it says this. It's really kind of a short problem. It says a uniform solid disk. So remember that. It's a solid uniform disk. And we know the moment of inertia of that shape, right? All right. A uniform solid disk is set into rotation with an angular speed omega I. So initial angular momentum. About an axis through its center. While it is still rotating at this speed, this disk is then placed into contact with a horizontal surface and released. A. What is the angular speed of the disk once pure rolling takes place? And then B. Find the fractional loss of kinetic energy from the moment the disk is released until pure rolling occurs. So I brought this wheel out for just this reason. So we can kind of see what this picture is saying. If we get and they say disk, so this isn't quite the same. I don't have a disk here. But if I get this thing rolling, some initial angular speed, what happens when I place it on the horizontal surface? Yeah, there's going to be some friction here. There's going to be some sliding. There's going to be some static friction, kinetic friction, until it starts pure rolling, right? And so as this thing is spinning, right here, there's skidding going on. That skidding makes some friction. That gives it a force. That's what gives it an acceleration that way, right? And so there is a translational acceleration. But at the same time, it's this force here that supplies a torque, which is slowing it down from spinning. And so if you watched, look at the spin rate. Doesn't the spinning slow down as the translational speed picks up? How do you solve this? Right? All right, so let's write out the equations. Again, all these problems, you've gotten to the level now that they're so involved and so complex, you're not going to even come close to guessing and figuring out that it's 1/3 the rotational speed. You've got to work it out here. And so you got to draw your free body diagrams. You've got to come over here and say, okay, here is this spinning disk. I'll keep it above the table for a moment. I've got it spinning. We'll say that is omega I. And so there's my initial angular speed of it. But the real key to the problem then is you are now going to let it touch the ground here. And when it touches the ground, it puts a force, and I'll call it a kinetic friction, as long as there's slippage going on, right? As long as there's sliding going on, this is going to have some friction here and make it go. Now, during that time period, what's going to end up happening is if we write down the equation for the translational motion, and also the corresponding equations for the rotational motion, you would say, okay, does this object have an acceleration? And maybe I should say an acceleration in the x direction. Yeah. As we write down the free body diagram, and I guess my free body diagram is not complete. I mean, there would be a normal force pushing up from the table. There would be a gravitational force pushing down. But I think you can see those are all in the y direction. What makes it move in the x direction? That force of friction, doesn't it? Divided by the m. Don't make this hard, right? Newton's second law. Add up all the forces. That's it. Does it have a speed? Yeah, well, the speed is what makes it have friction. So I guess I'm not saying that the speed isn't part of the problem, but that's not a new force. The fact that there is a rotation, and that's what they're after here, right? Just write it out. What force do you have? You have kinetic friction, right? That's going to make it have an acceleration. And here's what's nice about this one. You might be surprised for me to hear you say this, but here's what's going to make it easy. What do we know about kinetic friction? It's a constant value regardless of what it is, right? So when you first set it down, I would say there's a lot of motion between the wheel and the table. And a little bit later, less motion. But as long as there's some motion, isn't the force the same? And so isn't the acceleration the same? And so until pure rolling starts, don't you have a constant force and therefore a constant acceleration? And this will take us all the way back to chapters 2. What's nice about constant accelerations is, yeah, the final speed is equal to the initial speed plus the acceleration multiplied by time. And so there is our kinematics equation number 1 that was only valid for constant accelerations. And so if I take these two and put them together, I could say, okay, here's the final speed of that wheel. It is equal to the initial speed. Now, isn't the initial speed 0? The initial translational speed is 0. Is the initial rotational speed 0? No. So again, this is what makes it a magenta problem. We got to look at both at the same time. And at this point, I'm only looking at the translational motion. But this would be the force of friction divided by m multiplied by time. And so that would well describe the translational motion. What is going on with the translational motion? When I jump over here to the rotational motion, I would do the same thing. Does the wheel have an angular acceleration? Yeah? How would you calculate it? Would it be its torque divided by its rotational inertia, right? That's Newton's second law. So again, do the same thing. Write it out. You know, I'm sure at this point you're asking, how are these things going to be tied together? You don't know. Just don't ignore it. Just write it out. Keep working on it. And so in this case, what is the torque? Well, there's the force of friction at a distance of, if we call this r, the torque then is the force of friction at a distance r away. Fair enough? And if you want to put sine of 90 degrees, you can do that too. And what's the moment of inertia of this solid disk? 1/2. Let me use the same m. Did I use a capital or I used a lowercase? Okay, m r squared. So if we simplify this a little bit, we can put the 2 upstairs and cancel one of the r's. And so there would be my equation for the angular velocity. Now again, what's nice about this is, just like we had kinematics equation number 1, this is a constant force resulting in a constant torque. A constant torque means that the final angular speed is equal to the initial angular speed, and then I'm going to put plus or minus here just to make you think a little bit. It's alpha t, right? Now in this case, I don't know the final speed, but I do know it starts with an initial speed, so I don't know what that is. But let's say the initial speed is a positive number, which I know it's clockwise, and we don't usually call clockwise a positive number, but let's call a rotation this way positive, because that made the wheel go positive. And didn't we say that indirectly? Didn't we say this direction was positive? So my acceleration should be in the negative direction, right? Isn't this acceleration slowing the wheel down? It's opposite of the direction it's spinning. And if you want to do the right-hand rule, there would be r, there would be f, and I'd go r cross f, and I'd get out of the board. Okay? Which again, traditionally we call that one the positive one, but we're going backwards of that. I'm calling this rotation the positive, so out of the board is now a negative. So this is actually a negative acceleration. So I really calculated the magnitude of the acceleration. But I knew that, so I was careful down here not to mess with that. Okay? But the question is, what is the new rotational speed once pure rolling takes place? This is really what it's after. And what's nice about this is you can see that you have time. And you have time. So couldn't we solve this for time and put it into there? Because one of the things I really don't know about this is how much time did it take for pure rolling to take place? I mean, I dropped this on here and it started skidding. And it looked into my eyes that it went about this far, and I don't know how much time that was. It didn't look like it was more than a second, but it some fraction of a second. But I don't know the time. So if I solve this for time and put it into here, let's see what I get. I get final speed times m over force of friction is equal to time. If I put that into here, I get initial speed minus 2 force of friction m over r. Time would then be final speed multiplied by m over force of friction. And what's really nice, force of friction even goes away too. So by substituting time, which I don't know, gives me a chance to subtract off friction, which I also don't know. And okay, and masses cancel off too. That's kind of nice. Now I can keep working on that equation. Final speed is equal to then initial speed minus, and in the top I got a 2, and in the bottom I got a final speed over radius. Ooh.
So wouldn't that be negative?
Yeah, isn't that final angular speed? And now when I move it over to here, it's 3 times final speed is equal to initial speed. And so final speed is 1/3 of the initial speed. Yay! Right? And so I can answer A. What is the final speed of this? And I'm going to run out of time, but B was, what fraction is converted into heat? Wasn't there some heat here? Was this wheel was spinning? Wasn't there rubbing going on? So if I apply conservation of energy, I can say 1/2 I omega initial squared is how much energy I start with, right? Where does it go? Well, it goes into translational kinetic. Some of it is still rotational kinetic, and the rest is heat. And so I can solve for that one by putting in my known values here, this, maybe I will leave alone. This, I will write final speed as r squared times the final speed squared. But final speed squared, I just did over here. Final speed is 1/3 of the initial speed squared. And I'm going to be out of time, but you can see there is an initial speed squared. Oh, what'd I do? Here? Here. Ah, thank you. Final. Oh, and which means then this can be written as 1/3 initial speed squared. Blah, 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 blah. We're out of time there. But yeah, hopefully you can see it. Now that I've really cracked the puzzle right here. I've got 1/3. And once I got that, then I can do a bunch of algebra and substitutions and figure out how